Right now, somewhere on the surface of the sun, a magnetic field is twisting itself into a knot. In a matter of minutes, that knot will snap. When it does, it will release the energy of 100 billion atomic bombs and hurl a billion tons of charged plasma toward Earth at 3 million kilometers per hour. You are not going to feel it. You are not going to see it. Tonight, you will sleep safely, while the second largest explosion in our solar system bends quietly around you. You will sleep safely because of something you have never seen, a magnetic shield that began forming when our planet was still molten rock 4.5 billion years ago, and that has wrapped itself around every breath you have ever taken. If that shield failed tonight, the northern lights would be visible from Madrid, the southern lights from the Atacama Desert. Within 18 hours, every satellite in low Earth orbit would be dead. Within a week, parts of the global power grid would not exist anymore. But that is not what is going to happen, because tonight, something very old and very quiet stands between you and the Sunday. And tonight, we're going to walk slowly through that something. We are going to start at the surface of a star 150 million kilometers away, and we are going to follow a single charged particle all the way to the back of your own neck. We are going to find out what this shield actually is, how it was built, why it sometimes fails, and what happened to the last planet we know of that lost theirs. There is something that astronomers like to say quietly, almost reluctantly, because it sounds like a metaphor when it is in fact a literal description of where you are. You do not live near the Sunday, you live inside it. The thing you call empty space between you and that bright disk in the sky is not empty. It is filled with the outermost layer of the sun itself, a thin, electrically charged wind of particles that has been flowing outward from our star for billions of years. It passes through the Earth's orbit. It passes through Jupiter's orbit. It passes through Pluto's orbit. It only finally fades into the wider galaxy somewhere around 18 billion kilometers from where you are sitting tonight. That whole bubble has a name. Astronomers call it the heliosphere. And everything inside it, every planet, every comet, every asteroid, every spacecraft we have ever launched is technically inside the sun's atmosphere. We have only crossed the outer edge of this bubble twice. Both crossings were made by spacecraft that left the Earth half a century ago, traveling in opposite directions, and that have been moving steadily outward ever since. The Voyager probes were launched in 1977, Voyager 1 in early September, Voyager 2 a few weeks earlier in late August on a different trajectory. They were originally meant to study the outer planets, Jupiter, Saturn, Uranus, and Neptune, and after they had finished those primary missions, no one knew exactly what would happen to them. They would continue outward. They would gradually lose contact as they passed beyond the limits of the antennas and instruments of the era. They would, eventually, become silent objects, drifting through interstellar space, with no one listening to them anymore. That is not what happened. Both spacecraft are still in contact, faintly, after almost 50 years. The Deep Space Network, a global array of huge radio antennas built for exactly this kind of long-distance work, picks up their signals as a whisper, transmitted with the power of a refrigerator light bulb from a distance now greater than 24 billion kilometers. The data arrives slowly. Each bit takes more than 20 hours to cross the gulf at the speed of light. And the data shows, among other things, that the spacecraft have left the heliosphere. Voyager 1 crossed the heliopause, the outer boundary of the bubble, in August of 2012. Voyager 2 followed in November of 2018. At the crossing, the instruments on each probe recorded a sudden change in their environment. The solar wind, which had been blowing past them for 35 years, abruptly fell off. The density of cosmic rays, the high energy particles arriving from the rest of the galaxy, jumped. The magnetic field changed direction. The probes had passed from the sun's atmosphere into the wider interstellar medium. So when you go outside tonight and look up at the stars, you are not looking at the universe through a window of nothing. You are looking at it from inside the breath of a star. This is the first thing it helps to understand, because everything we are going to talk about tonight, every storm, every shield, every aurora, every collapse, begins with one simple fact. The sun is not over there. The sun is around you, and the sun is not still. If you could somehow stand in space far enough away that the entire sun fit comfortably into your field of view, and if your eyes could see the magnetic field that wraps around it, you would not see a smooth, glowing sphere. You would see something restless, something writhing. You would see arcs of plasma the size of continents, rising from the surface, bending, falling back. You would see darker patches drifting across the visible disk, each one the size of several Earths. You would see streamers of charged gas reaching out into the dark, never quite breaking free, never quite settling. The sun is a star, and stars are not the calm objects they appear to be from 150 million kilometers away. They are furnaces with weather. They have moods, they have cycles, they have storms. The reason you do not normally feel any of this is the same reason you do not normally feel the weather over the Pacific Ocean while you are sitting at a kitchen table in another hemisphere. It is far away, and there is something in between. For the Pacific weather, the thing in between is mostly distance and a few mountain ranges. For the sun, the thing in between is the magnetic shield we are going to spend the rest of the night exploring. But before we can describe a shield, we have to describe what it is shielding you from. And to do that, we have to talk about what is happening on the surface of a star. Because right now, on the side of the sun that is facing your hemisphere, something specific is unfolding. Plasma is rising from below in slow convective columns the size of Texas. Magnetic fields are tangling and untangling themselves on a scale no human mind has ever truly held. A spot is darkening somewhere near the solar equator, cooler than its surroundings by 2,000 degrees, marked as the foot of a magnetic loop that began forming weeks before any human noticed it. And in some of those loops, the tension is building, slowly, quietly, the way a violin string is tightened by a small hand, one careful turn at a time, until the string finally cannot hold the note anymore. That is where we are going next. If you find this kind of slow, deep exploration of the cosmos calming, or if you happen to be here on a night when sleep is not coming easily, you are welcome. There is no rush. Subscribing helps the channel grow, but it also tells me what kind of nights to keep building for. Something strange happens to the sun every 11 years. Astronomers noticed it in the 17th century, long before they knew what the sun actually was. In 1610, when Galileo first turned a telescope toward the morning sun and saw dark spots drifting across its face, the discovery was so shocking that some of his contemporaries refused to believe him. The sun was supposed to be perfect, unchanging, a symbol of divine permanence. And here was an Italian mathematician claiming that the symbol of permanence had blemishes that moved. He was right. The blemishes moved because the sun rotates, and the blemishes appeared and disappeared because the sun has weather. For 300 years after Galileo, astronomers counted those spots. They drew them, they charted them. They noticed that some years there were many, and some years there were almost none. And eventually, in 1843, a German amateur astronomer named Heinrich Schwabe announced that the spots followed a pattern. They peaked every 11 years. Then they faded. Then they returned. He had no idea why. It took another century to understand. The sun, it turns out, is a fluid magnet. And like all fluid magnets, it twists itself into tangles, releases those tangles, and starts twisting again. The 11-year cycle is the sun working itself into a knot and then untying it, working itself into the next knot, untying that one too, forever. There are also longer period anomalies in the record that nobody has fully explained. Between 1645 and 1715, for 70 consecutive years, the sun produced almost no sunspots at all. Astronomers of the period, including some of the best observers of the 17th century, equipped with the newly invented refracting telescope, kept careful logs. The logs showed weeks, then months, then years passing without any spots crossing the visible disk. The 11-year cycle, if it was still happening, was happening at a much weaker amplitude than usual. This period is now called the Maunder Minimum, after the British astronomer Edward Maunder, who first documented it in the late 19th century. The Maunder Minimum coincided with the coldest portion of what climatologists call the Little Ice Age, a period of unusually cool temperatures in Europe and North America, when the Thames froze regularly in winter, when Scandinavian glaciers advanced over farmland, when the growing seasons in Northern Europe shortened by enough to cause occasional famines. The correlation between a quiet sun and cool weather has fueled centuries of speculation about whether the two are causally connected. The scientific consensus today is that the link is real but weak. A quiet sun contributes slightly less total energy to the Earth, which can amplify other cooling factors, but the total solar variation between active and quiet cycles is only a fraction of a percent, not enough by itself to drive a little ice age. Volcanic eruptions, ocean circulation patterns, and other terrestrial factors did most of the work. A second-long quiet period, called the Dalton Minimum, ran from about 1790 to 1830. It was milder than the Maunder Minimum, but still showed clearly in the sunspot record. Since then, every cycle has produced at least the normal number of spots. We are currently near the peak of solar cycle 25. It began in 2019, reached its predicted maximum in 2024 and 2025, and is expected to fade gradually into the late 2020s before bottoming out around 2030. Forecasts of cycle strength are notoriously difficult. Cycle 25 has turned out to be more active than most forecasters expected, with several major flares already in the historical top 10s. Whether it will produce a once-in-a-century event before it ends, no one knows. The sun continues to behave like the sun, predictable on average, surprising in detail. We are currently near the peak of the cycle, the 25th such cycle since the careful counting began, and during peaks, the surface of the sun is at its most active. If you could see a sunspot up close, you would not see a stain. You would see a depression in the surface, slightly cooler than the surrounding plasma, where a powerful magnetic field is breaking through from the layers below. The spot looks dark because cooler plasma glows less brightly than the rest, but the magnetism inside that spot is so intense that it would crush a human-made magnet flat from 100 meters away. Most sunspots are larger than the Earth. The biggest ones in recorded history have been larger than Jupiter, and every sunspot is the foot of a loop. The magnetic field that breaks through the surface in one spot has to come back down somewhere. So sunspots almost always appear in pairs or in clusters, connected by invisible arches of magnetic force that rise hundreds of thousands of kilometers above the visible surface before bending back down. When you look at the sun in the right wavelength, the wavelength that responds to magnetism rather than to visible light, you do not see a smooth disk anymore. You see a tangle. You see something that looks more like the surface of a frozen ocean during a storm. Loops upon loops, arches upon arches. Whole regions of crisscrossing fields some thousands of times stronger than the magnetic field of the Earth. Most of those loops are stable. They form, they drift, they eventually fade. But sometimes, and this is where our story begins, two loops touch. When two oppositely oriented magnetic loops meet on the surface of the sun, they do something that, in human terms, looks like an explosion, but is in fact something much stranger. The lines of force snap. They reconnect into new configurations. And in doing so, they release energy that was being stored in the magnetic field itself. The energy of one of these reconnections on a typical day is roughly equivalent to a few million atomic bombs. The energy of a serious one on a bad day is hundreds of times that. We call these reconnections solar flares. They happen on the sun several times a week, even on quiet years. During cycle peaks like the one we are in, they can happen several times a day. The sun has been having them since long before there was an Earth to observe them. It will keep having them long after the human species has stopped looking up. Most of them you never notice. The energy goes out as light, as heat, as X-rays, as a wave of photons that arrives at Earth 8 minutes later and is dissipated harmlessly in our upper atmosphere. But some of them release something else along with the light. Some of them release matter. And those are the ones that matter to you tonight. The sun does not have a surface. If you could descend into it, there would be no up, no down, no walls. And that changes everything you are about to understand. What we call the surface of the sun is a region called the photosphere. It is not a boundary in the way the surface of the ocean is a boundary. It is simply the depth at which the plasma becomes thin enough for light to escape. Above this layer, photons fly outward freely toward us. Below it, photons are absorbed and re-emitted again and again, bouncing around in the dense interior for tens of thousands of years before finally working their way out. This is worth pausing on because it is one of the quietly astonishing facts about light. The sunlight warming the side of your face when you step outside on a clear morning was not born this week. It was born hundreds of thousands of years ago, in the core of the sun, where 4 hydrogen nuclei fused into a helium nucleus and released a single photon. That photon then had to travel from the core to the surface a distance of about 700,000 kilometers. And because the interior of the sun is so dense that the photon could only move a fraction of a millimeter before being absorbed again, the journey took, on average, 200,000 years. Once that photon finally reached the photosphere, the journey from there to your face took about 8 minutes and 20 seconds. So when you stand in the sunlight, you are standing in light that started moving outward through plasma when our ancestors were still figuring out how to control fire. But we are not interested in the slow light tonight. We are interested in something faster and something heavier. Just above the photosphere, the sun has an outer atmosphere called the corona. The corona is, in some sense, the most mysterious layer of the sun because it is much hotter than the surface below it. The photosphere sits at about 6,000 degrees Celsius. The corona, a few thousand kilometers higher up, can reach 1 to 3 million degrees Celsius. Heat moving upward from a cooler region is not something the rest of physics finds intuitive. Astronomers spent more than half a century arguing about why this happens. The answer, when it finally came in the last few decades, was that the corona is being heated by the magnetic field itself by a constant background hum of small magnetic reconnections, each one releasing a tiny amount of energy, all of them together cooking the outer atmosphere to temperatures that the visible sun cannot reach. It is in this superheated corona that the dramatic reconnections happen. Picture it this way. 2 giant magnetic arches stand near each other above the surface, like 2 bridges built next to one another but with their cables crossed. The plasma trapped in each arch is being held in place by the magnetic field. The arches are stable. but they are also under stress. Slowly, as the sun rotates and the deeper layers churn, the feet of the arches are pulled in different directions. The cables twist, the tension grows, and then the touch. When the two magnetic structures meet, they do not bounce off each other. They reconfigure. In a few seconds, the lines of force tear and reconnect into a new arrangement. Lower energy than the previous one, releasing all the difference as a sudden, brilliant pulse of radiation and accelerated particles. Some of that energy goes outward as light. We see it from Earth as a bright flash on the sun's disk, but some of it goes outward as a wave of plasma, a bubble of charged matter ripped free of the surface, carrying with it some of the magnetic field that used to hold it down. The bubble is now flying outward into the solar system, no longer attached to the sun, no longer constrained by its weight. This is what astronomers call a coronal mass ejection, a CME. A typical CME contains about 1 billion tons of charged matter. It leaves the sun moving at anywhere from 400 kilometers per second to 3,000 kilometers per second, depending on how violent the original reconnection was. The fastest ones, the ones we will keep coming back to tonight, can cross the distance from the sun to the earth in less than a day. The light from the flare arrives in 8 minutes. The mass arrives later, sometimes much later. And in the time between those two arrivals, something has a chance to prepare. A wind has been blowing from the sun toward your house your entire life. It is blowing tonight. It will not stop until the sun dies. The solar wind is the most easily forgotten fact about our solar system because we have no everyday way to feel it. It does not move trees. It does not push clouds. It does not whistle through cracks in windows. Almost everyone who has ever lived has spent their entire life inside it without knowing. It begins in the corona, where the sun's outer atmosphere is so hot that even its gravity cannot hold the lightest particles down anymore. Electrons and protons stream away from the surface in all directions, accelerated to speeds of a few hundred kilometers per second, and they keep going. They thin out as they spread. By the time they reach the orbit of Earth, the density has fallen to about 5 particles per cubic centimeter, almost nothing, less than the best vacuum we can produce in a laboratory. But it is not nothing. It is a continuous, low-density rain of charged matter moving outward at 400 kilometers a second. It carries with it a piece of the sun's magnetic field, frozen into the plasma the way leaves are frozen into the surface of a winter pond. When a coronal mass ejection erupts from the sun, it does not move alone through empty space. It moves through the solar wind. It is a denser, faster, more magnetized bubble pushing into a calmer ambient flow. That ambient flow is the reason CMEs take so long to reach us. The light from the original flare crosses the sun-Earth distance in just over 8 minutes. The CME, which is matter rather than light, has to plow through everything in between. If the CME is slow 350 kilometers per second, just a little faster than the background solar wind, it can take 3 or 4 days to reach us. If it is fast 2,000 kilometers per second or more, it can arrive in under 20 hours. The fastest one ever recorded, in 2012, narrowly missed the Earth and took just under 17 hours to cross our orbit. If we want to put a number on it that holds for most serious storms, the answer is roughly 18 hours. 18 hours between a violent reconnection on the sun and 1 billion tons of charged matter slamming into the magnetic shield around our planet. 18 hours is not much, but it is something. It is enough time for a spacecraft watching the sun to detect the flare. It is enough time for that spacecraft to send the data home at the speed of light. It is enough time for forecasters at agencies in Colorado and Belgium and Japan to look at the magnetic orientation of the ejected matter to estimate when it will arrive and to issue warnings to the satellite operators and power grid managers who need to know. It is even enough time in a serious event to shut down certain systems, to put some satellites into safe mode, to reroute polar flights, to adjust the load on the most vulnerable transmission lines. That 18-hour warning, however, does not arrive on its own. It exists because over the past 5 decades, the human species has built a small constellation of robotic sentinels whose only job is to watch the Sunday. Some of them watch from low Earth orbit. The Solar Dynamics Observatory, an American satellite launched in 2010, photographs the sun every 12 seconds in 11 different wavelengths. Each frame is the equivalent of a high-resolution medical scan of the entire visible disk of the sun, taken in the parts of the spectrum that respond to different temperatures and to different magnetic structures. SDO has produced more data than any other single solar observatory in history. Most of it has never been looked at by human eyes. There is too much. Automated systems comb through the imagery, flagging the events that need attention. Other sentinels watch from much farther away, about 1.5 million kilometers from the Earth in the direction of the sun. There is a gravitational sweet spot called the L1.A, location where the gravity of the Earth and the gravity of the sun balance in such a way that a small spacecraft can orbit stably around that point indefinitely. At L1, a satellite has an unobstructed view of the sun and a continuous direct path back to Earth for radio communication. It is, for the purposes of solar physics, the best seat in the inner solar system. 2 spacecraft sit at L1 today. The older one, ACE, the Advanced Composition Explorer, launched in 1997, carries instruments that measure the chemical composition and magnetic properties of the solar wind as it arrives at the L1 point. The newer one, DSCOVR, the Deep Space Climate Observatory, launched in 2015, also monitors the incoming solar wind and adds a continuous view of the daylit side of the Earth as a calibration baseline. Both spacecraft serve as tripwires. When a CME passes through the L1 point on its way toward the Earth, instruments on board immediately detect the change in the local plasma environment. The data is transmitted to Earth at the speed of light, taking about 5 seconds to arrive. The CME itself, traveling at perhaps 1,000th of the speed of light, will take another 30 to 90 minutes to cover the same remaining distance. That gap between the warning and the impact, a half hour to 90 minutes, is the most reliable part of the 18-hour warning. Other parts of the prediction, based on observations of the original flare and on theoretical models, are useful but uncertain. The CME could be slower or faster than predicted. Its magnetic orientation, which determines how dangerous it will be, cannot always be measured accurately until it reaches L1. The L1 tripwire is the moment when all of the uncertainty collapses, when forecasters finally know what is about to hit the planet. 30 to 90 minutes is not a long warning. It is enough time to put critical satellites into safe mode. It is enough time to alert grid operators to be ready. It is not enough time to evacuate or rebuild anything. The infrastructure either holds or it does not. For most of the time, the L1 tripwire has existed. It has held. But sometimes, the orientation is exactly right. A CME has its own magnetic field, dragged out of the sun along with the matter. When that field arrives at Earth pointing in the same direction as our own, when the southern end of the CME's field meets the northern end of Earth's, the two fields cancel each other out at the boundary. The shield, in that moment, becomes thinner, easier to push against, easier to disturb. That is when the energy of the CME starts pouring into our magnetic field. That is when the shield starts ringing. That is when, deep inside the Earth's atmosphere, things start happening that no one can quite see, but that machines can measure with terrible precision. And in extreme cases, that is when transformers melt and continents go dark. We will come back to that. We will come back to it twice. But first, we have to walk down. Down past the atmosphere, down past the crust, down into the place where this shield begins. Because the magnetic field of the Earth, the thing that has been deflecting solar storms quietly around you for every minute of your life, is not a property of the surface. It is not generated by the rocks beneath your feet. It is not stored anywhere visible. It is being made right now by something 3,000 kilometers below you. And if that something ever stopped, you would have a much bigger problem than a single solar storm. 3,000 kilometers below your feet, something is spinning. If it ever stopped, this story would end. Below the surface of the Earth, below the soil and the limestone and the granite, below the slow-moving plates of the crust, below the partially molten mantle that drags those plates around like rafts on tar, there is a place where the temperature is hot enough to melt iron and the pressure is great enough to crush it. 2,900 kilometers down, the mantle ends and the outer core begins. The outer core is not solid. It is a thick, hot ocean of liquid iron and nickel, about 2,200 kilometers thick, that wraps entirely around the small, solid inner core at the very center of the planet. The iron in the outer core is heated from below by the inner core and cooled from above by the mantle. It convects, it rises, it sinks, it flows in great looping currents that take centuries to complete a single rotation. How do we know all of this? When no one has ever traveled more than about 12 kilometers below the surface. The deepest hole ever drilled, the Kola super deep borehole in northwestern Russia, abandoned in 1995, reached only about a third of the way through the crust before the temperatures and pressures defeated the drilling equipment. The mantle, 3,000 kilometers thick, has never been directly sampled. The outer core, beneath the mantle, has never been touched by anything human. We know the structure of the interior of the Earth because of earthquakes. When an earthquake happens at one point on the surface of the planet, the energy of the rupture radiates outward in the form of seismic waves. Some of those waves travel along the surface, others travel straight through the Earth's interior, eventually emerging at distant points on the opposite side. Two main types of internal waves exist. Pressure waves, called P waves, are faster and can travel through both solids and liquids. Shear waves, called S waves, are slower and can travel only through solids. They cannot propagate through a liquid because liquids have no shear strength to support the wave motion. In the early 20th century, seismologists began noticing something strange about the patterns of waves from large earthquakes. P waves reached every point on the planet, but with strange delays at certain angles. S waves stopped arriving at certain distances from the original earthquake. Whole regions of the planet's surface received P waves, but no S waves at all. These regions, called shadow zones, formed roughly ring-shaped patterns around each earthquake. The interpretation was clear, even if at first it was hard to believe. The S waves were being blocked by a liquid layer deep inside the Earth. The P waves were getting through that layer but being refracted, bending as they crossed it, the way light bends as it crosses a glass water boundary. Somewhere in the interior of the planet, the material had to be liquid. By the 1930s, the picture had been refined further. A Danish seismologist named Inge Lehmann noticed that some P waves were arriving in places that the liquid outer core model said should be shadow zones. The simplest explanation, she argued in a 1936 paper, was that the liquid outer core itself contained a smaller, solid inner core at its center. The new model required that the iron at the very center of the Earth, despite being far hotter than the iron above it, was solid because of the immense pressure squeezing it into a crystalline structure. Lehman's model has held up. The boundary between the liquid outer core and the solid inner core sits about 5,150 kilometers below the surface. The inner core itself is roughly the size of the moon. We know it is there, and we know its boundaries, and we know its composition reasonably well because of how seismic waves from earthquakes thousands of kilometers away bend and reflect off it. And because liquid iron conducts electricity, those flowing currents, combined with the rotation of the planet, generate a magnetic field. This is the dynamo, the geomagnetic dynamo, the single physical process that is responsible for everything you are about to learn. The mathematics of a dynamo is complicated, but the physical intuition is reachable. A moving conductor in a magnetic field generates an electric current. An electric current in a moving conductor generates a magnetic field. If you set the conductor up right, if it is large enough, hot enough, conductive enough, and moving in the right way, these two effects can sustain each other indefinitely. The conductor generates the field that sustains the current that maintains the field. It is a self-reinforcing loop, powered entirely by the heat trying to escape from the planet's interior. For most of Earth's history, that loop has been running. It started about 3.5 billion years ago, sometime after the planet had cooled enough to form a stable iron core, but while there was still enough internal heat to drive vigorous convection, it has not, as far as we can tell, stopped since. Through ice ages, through asteroid impacts, through the rise and fall of every species that has ever existed, the iron has continued to flow. The result, at the surface, is a magnetic field that we can measure with simple compasses, but whose true shape is much stranger than any compass can show. If you could see the field, you would see it leaving the Earth near the geographic South Pole, sweeping out into space in a series of curved lines, wrapping back around, and re-entering the Earth near the geographic North Pole. The lines would not be straight, they would not be evenly spaced, they would bulge outward in certain places and dip inward in others, reflecting irregularities in the deep flows of iron below. But the overall pattern would be roughly that of a bar magnet, tilted about 11 degrees from the planet's rotational axis. This is the dipole field. It is the part of the geomagnetic field that reaches the farthest into space, and it is the part that does most of the work of deflecting the solar wind. The strength of the field at the surface is small, about 30 to 60 microtesla, depending on where you are standing. A refrigerator magnet is something like 100 times stronger. You cannot feel the geomagnetic field. You cannot detect it without instruments. If you held a compass loosely, you would notice it tugging the needle. That is the most direct sensory experience of it most humans ever have. And yet this faint, invisible, refrigerator magnet weak field, projected outward across tens of thousands of kilometers, is the thing that has been deflecting an unbroken rain of solar particles around you for your entire life. How does something so weak do something so important? The answer is geometry. The field is weak at the surface, but it extends an enormous distance into space. And out there, far from the Earth, where the solar wind arrives, the field is reshaped by that wind into something that no laboratory could ever build. The interaction between the solar wind and the geomagnetic dipole creates a structure that does not exist in any other context in nature on this planet. That structure is a teardrop-shaped bubble around the Earth, a bubble large enough to contain the moon's orbit on its day side and to stretch out behind us for millions of kilometers on the night side, a bubble that has a name, the magnetosphere. And the magnetosphere is what we're going to walk through next. Imagine a bubble. The bubble you are living inside of right now is called the magnetosphere, and it is shaped like a teardrop. On the day side of the Earth, Where the solar wind is constantly pushing inward, the magnetosphere is compressed. The boundary of the bubble sits about 65,000 kilometers above the daytime surface, roughly 10 Earth radii out. On the night side, where there is no solar wind pressing in, the magnetic field stretches out behind us into a long tail that reaches at least 300,000 kilometers into space, sometimes much further. Some measurements have detected the magnetic tail of the Earth at the orbit of the Moon, 384,000 kilometers away. There are theoretical reasons to think it goes even further. Inside this bubble, almost no solar wind particles can reach you directly. The geomagnetic field deflects them around the outside of the bubble like a stream of water flowing around a stone. They sweep past us, over us, around us, and continue into the dark. This is the protection, this is the shield, but the shield is not a wall. It is not solid. It is not even continuous in the way a soap bubble is continuous. It is a region of space where the rules are different, where charged particles, which can fly in straight lines through empty space, suddenly find themselves following curved paths because the magnetic field exerts a force on them at every step. To understand how this works, you have to understand one specific physical fact about charged particles in magnetic fields. A charged particle moving through a magnetic field experiences a force perpendicular to its motion. It cannot move in a straight line. It is forced to spiral. The direction of the spiral depends on the charged positive particles. Spiral one way, negative particles the other. The tightness of the spiral depends on the strength of the field and the speed of the particle. This means that when a proton from the solar wind, moving at 400 kilometers a second, encounters the Earth's magnetic field, it cannot simply plow through. It is deflected. It curves. If the field is strong enough at that point, the particle is turned aside and sent traveling along the boundary of the magnetosphere, never penetrating it, eventually rejoining the solar wind on the far side of the planet. A particle that approaches the magnetosphere at exactly the right angle and exactly the right speed might slip in, but most particles do not. Most particles are turned away. The shape of the bubble matters here. On the day side, the field is compressed and strong, and almost no particles get through. On the night side, the magnetic tail is much weaker per unit volume and more complicated structurally, and that is where things become interesting. But before we get to that complication, it is worth pausing on the shape itself. Because the magnetosphere does not look like the simple bar magnet diagrams we draw in school textbooks. It is asymmetrical. The day side is squashed close to the Earth, sometimes pushed in to within 40,000 kilometers of the surface during severe storms. The night side is drawn out into a long, slowly tapering tail, with magnetic field lines that point in opposite directions on the two halves of the tail, and that meet in a thin sheet of electrical current down the middle. It also has a fascinating boundary on the day side. As the solar wind sweeps in at 400 kilometers a second and meets the Earth's magnetic field for the first time, it does not gradually slow down. It hits a kind of wall. A standing shock wave forms in space, about 90,000 kilometers above the daytime surface, where the supersonic solar wind suddenly drops to subsonic speeds. Physicists call this the bow shock. Beyond it, in the direction of the sun, the solar wind is still flowing freely. Inside it, between the shock and the magnetosphere itself, the wind is slower, denser, hotter, and more turbulent. This region is called the magnetosheath. Earth's magnetosphere, while elegant and protective, is not the largest one in the solar system. That distinction belongs to Jupiter. Jupiter has a magnetic field roughly 20,000 times stronger than ours at its surface, generated by a deep ocean of metallic hydrogen. Hydrogen compressed to such extreme pressures that the electrons stop belonging to individual atoms and start flowing freely, the way they do in metals. That ocean of metallic hydrogen is also a fluid conductor, also convecting, also producing a dynamo on a scale that dwarfs the Earth's iron core. The result is a magnetosphere so large that, if you could see it in the night sky from Earth, it would appear several times larger than the full moon. Jupiter's magnetic shield extends about 7 million kilometers in the sunward direction. On the night side, the magnetic tail stretches out far enough to reach the orbit of Saturn, hundreds of millions of kilometers away. Inside that immense bubble, Jupiter's largest moons orbit Io, Europa, Ganymede, Callisto, and the radiation environment surrounding them is one of the harshest in the solar system. The Galileo probe that orbited Jupiter from 1995 to 2003 absorbed radiation doses many times the lethal limit for a human being. The spacecraft survived only because its electronics had been hardened beyond anything previously built. Future missions to Europa, with its possible subsurface ocean, will have to be designed with the same kind of armor. The point of mentioning Jupiter is not to make the Earth's magnetosphere seem small by comparison. The point is to show that magnetospheres are not exotic. They are a common feature of planets with conducting fluid interiors and reasonable rotation rates. Saturn has one, Uranus has one, though tilted strangely with respect to its rotational axis. Neptune has one. Even Mercury, the smallest planet, has a small, weak magnetic field that maintains a tiny magnetosphere despite its proximity to the Sunday. The planets that do not have global magnetic fields in our solar system are the ones that have lost them. Mars, as we will see at the end of tonight, used to have one. Venus may have had one briefly, billions of years ago. Both have surfaces that are now exposed in ways the Earth is not, to the unfiltered solar wind. There is a place about 65,000 kilometers above the day side of the Earth where the solar wind and the magnetic field meet for the first time. And when they meet, there is a sound. Not a sound any human has ever heard with their ears, but a sound in the precise sense that there are pressure waves moving through the plasma, oscillations rippling outward, frequencies that can be picked up by the right kind of antenna on the right kind of spacecraft and converted into something we would recognize as audio. When researchers at the European Space Agency translated those magnetic oscillations into sound a few years ago, the result was eerie. It sounded like a choir of distant whispers, voices half heard, a continuous, restless murmur of plasma colliding with field, held together by physics older than the species that built the antennas. That is the sound of the shield working. And inside the shield, where the deflected particles still sometimes manage to slip through, there are places where things accumulate. Places where the same field that turns particles aside can also trap them. We are going to look at those next. We just touched briefly on the bow shock. We are going to slow down and look at it carefully now, because the bow shock is one of the strangest places in the immediate neighborhood of the Earth, and almost no one outside of plasma physics knows it exists. The solar wind, you will remember, is moving at about 400 kilometers per second on a typical day, and faster than that during storms. That is roughly 40 times the speed of a high-velocity rifle bullet. But because the medium it is moving through is so thin, and because the relevant comparison is not to sound in air but to the speed of waves in plasma, this is technically supersonic. The wind is moving faster than waves in plasma can travel. When a supersonic flow encounters an obstacle, it cannot adjust gradually. It cannot send signals upstream to warn the flow ahead that something is in the way because the signals travel slower than the flow. The result is a shock, a sudden, sharp boundary where the flow drops to subsonic speed in a tiny distance, and where the temperature, density, and magnetic field all jump up. This is what happens to the solar wind when it meets the magnetosphere. About 90,000 kilometers above the day side of the Earth, the solar wind hits this invisible wall. The wall is not a wall in the sense of being solid. It is a thin layer, maybe a few hundred kilometers thick, where the plasma is suddenly compressed, heated, and slowed. The wind that emerges on the inside of the bow shock is hotter, denser, and more chaotic than the wind that arrived. It then has to flow around the magnetosphere, sliding along the outside of the bubble like water around the prow of a slow boat, eventually reuniting downstream and continuing on into the dark. This is happening continuously, right now. As you read this, above your hemisphere, a wall of plasma is shaping the wind from a star. Spacecraft have crossed this boundary many times. The first one was an American satellite called Explorer 12 in 1961, which detected a sudden change in the magnetic field as it moved outward through the day side of the magnetosphere. Since then, dozens of spacecraft have flown through the bow shock in different directions and at different times. We have a fairly detailed map of where it sits and how it moves. During solar storms, the bow shock is pushed inward, sometimes by tens of thousands of kilometers. During quiet periods, it relaxes outward. It breathes in slow rhythm with the activity of the Sunday. Beyond the bow shock, between the shock and the surface of the magnetosphere proper, there is a turbulent region called the magnetosheath. The magnetosheath is where the slowed, heated solar wind piles up before slipping around the Earth. It is the calmest violent place in our cosmic neighborhood. The particles there are moving relatively slowly, but they are very hot temperatures of millions of degrees. They cannot reach you. The next boundary, the magnetopause, the actual surface of the magnetosphere, turns them aside. The magnetopause is where the pressure of the solar wind exactly balances the pressure of the Earth's magnetic field. It is the true edge of the protective bubble. Inside the magnetopause, the geomagnetic field dominates. Outside it, the solar wind dominates. The boundary itself moves in and out with the strength of the wind. On a calm day, the dayside magnetopause sits about 10 Earth radii out about 65,000 kilometers. On a stormy day, it can be pushed into 6 Earth radii. On the worst recorded day in space-age history, in March of 1989, the magnetopause was pushed inside the orbit of some geosynchronous satellites about 36,000 kilometers from the surface. And those satellites suddenly found themselves outside the protective bubble of the Earth, naked in the solar wind, exposed to a rain of high-energy particles their designers had not expected them to encounter. Some of those satellites recovered when the storm passed, some did not. We will get to that night. But for now, picture the bubble. Picture the wall 90,000 kilometers out, where the supersonic wind from a star slows down. Picture the magnetosheath behind it, hot and turbulent. Picture the magnetopause 65,000 kilometers out, where the calm interior begins. Picture the long tail stretched out behind you into the dark, where the moon's orbit lies and where the wind has long since gone. You are sitting inside that bubble. You have always been sitting inside it. And almost everything moving in space around your planet, every satellite, every astronaut, every speck of debris, every grain of cometary dust exists in some particular position within this giant invisible structure, shaped by the same forces, including the strange donut-shaped regions of trapped particles that lie inside the bubble, including the cages of light. If you have stayed with me this far, you are exactly the kind of person this channel was built for. Subscribing costs you nothing, and it helps me keep making these long, slow journeys for the nights when nothing else helps. Inside the protective bubble of the magnetosphere, there are 2 regions where the geomagnetic field does something different. It does not deflect particles past us, it captures them. These are the Van Allen belts, named after the physicist James Van Allen, whose instrument on the first American satellite, Explorer 1, detected them in 1958. The discovery was so unexpected that Van Allen's team initially thought their counter had broken. The Geiger counter was supposed to register a few hits per second from cosmic rays. Instead, at certain altitudes, it suddenly reported 0 counts. Then, a few seconds later, at a slightly lower altitude, it returned to normal. The counter had not broken, it had saturated. There were so many particles in that region of space that the instrument could not keep up. When it counted faster than it could process, its electronics simply gave up and reported nothing. What Van Allen had discovered was a donut-shaped region around the Earth where charged particles, mostly protons and electrons, were trapped in enormous numbers, spiraling along the magnetic field lines at high speed, bouncing back and forth between the northern and southern hemispheres for years or decades at a time. There are 2 main belts. The inner belt sits about 1,000 to 12,000 kilometers above the equator and is dominated by high-energy protons. The outer belt sits roughly 13,000 to 60,000 kilometers above the equator and is dominated by high-energy electrons. Between them, in a relatively empty zone called the slot, the particle density drops by orders of magnitude. The mechanism that traps these particles is the same one that deflects the solar wind around the magnetosphere. A charged particle in a magnetic field cannot move freely. It spirals. If the field has the right shape, if it converges toward 2 points, the way the geomagnetic field converges toward the magnetic poles, then a particle spiraling toward one pole will eventually find itself in a region of stronger field. As the field strengthens, the spiral tightens, and the forward motion of the particle slows. Eventually, the particle stops moving forward along the field line entirely. It reverses direction. It begins spiraling back the other way toward the opposite pole, where the same thing happens again. The particle is now trapped. It bounces back and forth, North Pole to South Pole, and back again, completing a full bounce in a fraction of a second. Meanwhile, the curvature of the Earth's field also causes the particle to drift slowly around the planet eastward for electrons, westward for protons, completing a full lap of the Earth in a few minutes to a few hours, depending on its energy. A particle in the Van Allen belts can stay trapped for years. The fastest electrons in the outer belt move at close to the speed of light. The most energetic protons in the inner belt carry the energy of a small bullet, concentrated in a single particle weighing essentially nothing. These belts are one of the reasons that human spaceflight is harder than it looks. Astronauts on the International Space Station orbit at about 400 kilometers, well below the inner belt, and so they are mostly protected from these high-energy particles. But any spacecraft that goes higher, every satellite in medium Earth orbit, every probe to the moon, every mission to Mars has to pass through the belts. The crews of the Apollo missions to the moon flew through the belts twice, once outbound and once on return. They timed their trajectories to minimize their exposure, and they wore no shielding beyond the walls of their spacecraft. And the doses they received were significant, but not catastrophic. If they had lingered in the belts, instead of passing through them in a few hours, the doses would have been lethal within days. The belts are also where solar storms do some of their most interesting and destructive work. During a major geomagnetic disturbance, the energy pouring into the magnetosphere from the solar wind accelerates the particles already trapped in the belts to even higher energies, and adds new particles from outside. The outer belt, in particular, can swell to many times its normal density within hours. Satellites that were operating safely in low-density regions of the outer belt can find themselves after a storm embedded in a sea of high-energy electrons. Those electrons penetrate the spacecraft's skin, accumulate inside electronic components, and eventually discharge, sometimes releasing themselves in a sudden spark that destroys a critical circuit. This phenomenon has a name: internal charging. It has killed satellites. It has cost insurance companies billions of dollars. It is one of the reasons that every modern satellite carries dosimeters that measure the local radiation environment in real time, so that operators can shut down sensitive components before the dose becomes lethal to the hardware. The belts respond to the sun in other ways too. After a major storm, they sometimes reorganize themselves into entirely new structures. In 2012, a Hubble-class space telescope called the Van Allen probes detected a third radiation belt, sandwiched between the usual two, that had formed in the wake of a particularly violent solar event. The third belt lasted 4 weeks, then it dissipated. We do not fully understand why it appeared or why it vanished. We only know that the belts are not stable structures. They are constantly being shaped and reshaped by the activity of the Sunday. This is part of the strange double nature of the magnetic field around the Earth. It is a shield, but it is also a trap. It deflects particles around us, but it also captures particles that get inside. It protects the surface, but it accumulates a slow archive of solar weather in the form of trapped electrons, spinning silently through the dark a few thousand kilometers above your head. And once in a while, when a serious solar storm arrives, some of those trapped particles and some of the new ones that came with the storm find their way down to the upper atmosphere. They follow the field lines toward the poles, accelerating as the field converges, until they slam into the thin gas at the top of the sky. When they do, the sky lights up. There is one place where you can see the shield working with your own eyes. You have to be in the right place, close enough to the magnetic poles that the field lines come down through the upper atmosphere near you, far enough from city lights that the sky is genuinely dark. You have to be there on the right night, usually a night a day or two after a strong solar event, when the magnetosphere is still ringing from the impact of a coronal mass ejection. You have to look up, and if all of that is true, you will see something that humans have been seeing for as long as there have been humans living near the polar regions, and that we did not understand the cause of until the 20th century. You will see the sky on fire, not with the orange and red of an actual fire, but with shifting curtains of green and pink and violet, draped across the dark from horizon to horizon, rippling slowly as if something invisible were stirring them with a long, gentle hand. The colors fade in and out. The shapes move. Sometimes, if the storm is strong enough, the whole sky overhead becomes a moving sheet of light. Sometimes you can almost convince yourself that you can hear a sound from it, though instruments tell us this is mostly an illusion of the brain, fed by the visual intensity of what is happening above. These are auroras, the northern lights in the Arctic, the southern lights, the aurora australis, in the Antarctic and in the very high southern latitudes. The mechanism, in physics terms, is simple. A charged particle, accelerated by the geomagnetic field, slams into a molecule of oxygen or nitrogen in the upper atmosphere. The collision excites the molecule, kicking one of its electrons into a higher energy level. After a moment, the electron drops back down, and the molecule releases the difference as a photon of light. The color of the photon depends on which molecule was excited and how it was excited. Oxygen struck at altitudes between 100 and 200 kilometers releases green light. This is the dominant color of most auroras. The green of the northern lights is the color of oxygen relaxing after being kicked. Oxygen struck at higher altitudes 200 to 300 kilometers releases red light. Red auroras require both stronger storms to send particles that high and lower atmospheric density so that the excited molecule has time to release its photon before it collides with another molecule and loses the energy in some other form. Nitrogen struck at lower altitudes releases blue and pink and purple. These colors are rarer, and they tend to fringe the lower edges of auroral curtains, just below the bright green main body. Put it all together, and the aurora becomes a real-time chemical analysis of the upper atmosphere, performed by particles that were ejected from the sun several days ago, accelerated through the magnetosphere, funneled down along the converging magnetic field lines toward the poles, and ultimately deposited as a brief flash of color in a layer of gas that humans have never directly touched. The latitude at which auroras appear is not random. It depends on the strength of the geomagnetic storm. On most nights, the auroral oval, the ring around each magnetic pole where auroras are most likely, sits at high latitudes. Northern Norway, Iceland, northern Canada, southern New Zealand, Tasmania. During moderate storms, the oval expands toward the equator. Auroras might be visible from Scotland, from the northern United States, from southern Australia. During severe storms, the oval expands much further. Auroras have been recorded as far south as the Caribbean, visible in the morning twilight from countries that do not usually associate themselves with the polar lights. The most famous example of this came in 1859. We will get to that. But the everyday aurora is itself a remarkable thing, because what you are watching when you stand outside on a cold night in northern Norway and the green light begins to move across the sky is not just a pretty atmospheric phenomenon. You are watching the magnetic shield of your planet performing its most important function. You are watching it absorb the energy of a star, transfer that energy down 120 kilometers of magnetic field line, deposit it in the upper atmosphere, and dissipate it as light. That light is not the storm. That light is the storm being safely converted into something harmless. If the auroras were not there, the energy would still arrive. It would just arrive somewhere else and as something else. Lower in the atmosphere, as current induced in long conductors at the surface, as voltage spikes through transformers, as heat in the ionosphere, as all of the slower, less visible, more damaging consequences that we will look at in detail in just a moment. The aurora is the safe failure mode. The aurora is the shield bleeding off the storm. For the cultures that have lived under the auroral oval for millennia, the Sami in Scandinavia, the Inuit in the Arctic, the indigenous peoples of Siberia and Alaska, the lights have always carried meaning. They were ancestors. They were spirits. They were warnings. In some traditions, they were the souls of the dead, dancing. In others, they were the breath of an enormous animal. The interpretations varied. The fact of the lights did not. What changed in the modern era is that we eventually understood what they actually are. And once we understood, we began to use them. Auroras can be photographed from satellites. The shape and intensity of the auroral oval, viewed from above, is one of the clearest real-time measurements of how a geomagnetic storm is unfolding. When the oval expands, the storm is intensifying. When it contracts, the storm is fading. When it begins to break up into smaller pieces, energy is being deposited in unusual ways, and the consequences at the surface may be unusual too. There are also auroras that no model fully explains. In 2016, a group of amateur aurora photographers in Alberta, Canada, began posting images of a strange, luminous structure that did not look like a normal aurora at all. It was a narrow ribbon of mauve and white light oriented east to west across the sky. often appearing well south of the main auroral oval, sometimes accompanied by a row of green vertical bars beneath it that resembled a glowing picket fence. The amateurs called it Steve. For no particular reason, the name was a joke taken from a movie. The joke stuck. Professional researchers, intrigued, eventually took the name seriously and backronymed it to Steve Strong Thermal Emission Velocity Enhancement. Steve is not an aurora in the traditional sense. The colors are wrong, the location is wrong, the mechanism, when researchers finally began to investigate it with proper equipment, turned out to be different. Where normal auroras are caused by charged particles falling down field lines and exciting atmospheric molecules, Steve appears to be caused by a hot, fast-moving river of plasma flowing through the upper atmosphere at altitudes of around 450 kilometers. The plasma flow is so energetic that it heats the surrounding atmosphere to thousands of degrees, and the heated atmosphere glows. The exact details are still being worked out. The picket fence structures beneath the main Steve ribbon may be a separate phenomenon, possibly related to electromagnetic waves in the ionosphere, possibly something else. What Steve shows is that we do not yet have a complete catalog of what the upper atmosphere does when it is excited by a magnetic storm. There are subtler phenomena, fainter phenomena, briefer phenomena that careful observers can still discover. Citizen scientists, equipped with modern digital cameras and an internet connection, are noticing things that the professional satellites overhead, with their narrow fields of view and their predetermined targets, sometimes miss. The sky over your head on a stormy night near the auroral oval is still capable of doing things that no equation has yet fully described. But for someone standing in the dark in a high latitude on a clear night after a solar event, none of that matters. What matters is that the sky is moving, that something far older than the human species is being made briefly visible, that you are, for a few minutes, watching the planet protect itself. The shield, glowing. Most nights, the shield does its work invisibly. But sometimes, the storm is too big. On the night of September 2nd, 1859, a telegraph operator in Boston disconnected the batteries from his machine. The machine kept working. Frederick Royce, the operator, had spent the day struggling. Strange voltages were appearing on the lines. Sparks were arcing between connections. Messages were being garbled, lost, or arriving in slightly the wrong order. The telegraph network, which by that point was already a continent-wide system stretching from the eastern seaboard to the frontier, was misbehaving in ways that no one had a vocabulary for. By evening, Royce had decided that the batteries powering his portion of the line were unstable. He unhooked them and tried to send a message to Portland, Maine, expecting that nothing would happen. To his astonishment, the message went through. The current was coming from somewhere else, from the line itself. Across the country, similar things were happening. In one office in Pittsburgh, paper notes caught fire from the heat of the sparks jumping between equipment. In another, two operators in different cities continued their conversation for over 2 hours, using only the natural current that the wires were producing on their own. In a Norwegian office near the Arctic Circle, an operator wrote in his log that the lights were so bright outside that he could read by them. The stories from outside the telegraph offices were, in some ways, even more remarkable. On board a Union steamship in the Caribbean, the captain initially mistook the auroral glow on the northern horizon for a sunrise that had come hours too early. He ordered the watch to confirm the time. The time was 3 in the morning. The horizon was glowing red, as if a distant city were on fire. In the gold rush camps of the Rocky Mountains, miners woke up at 1 in the morning thinking it was already dawn, made breakfast, and were halfway through their morning routines before realizing the sky was glowing for some reason other than the Sunday. In some camps, full prospecting teams started out for the streams. In one settlement in California, the cooks reported finishing breakfast just as the brightness began to fade and the actual dawn started hours later. In many countries with strong religious traditions, the auroras were interpreted as signs. In the southern United States, several churches in cities that had never before seen the northern lights organized impromptu services, with congregations gathering in the streets to pray under the moving curtains of red and green. In rural communities in Mexico, in Colombia, in Cuba, similar gatherings happened spontaneously. The lights were too unusual and too vivid to be ignored, and the interpretive frameworks of the time made them meaningful in religious terms first, scientific terms later, if at all. In Boston, an editor at one of the major daily newspapers reported, in the next morning's edition, that the auroral light had been bright enough to allow him to read fine newspaper print at midnight without any artificial illumination. Witnesses across the eastern seaboard reported similar things bright enough to read books, to walk safely without lanterns, to see colors on objects normally only visible in daylight. What no one in any of these offices yet understood was that they were experiencing the surface consequences of the largest geomagnetic storm in recorded human history. 2 days earlier, on August 28th, an English astronomer named Richard Carrington had been doing routine sketches of sunspots from his observatory in Surrey when he saw something he had never seen before. 2 patches of intense white light, brighter than the visible disk of the sun itself, had suddenly appeared in the middle of a sunspot group. The patches lasted about 5 minutes, traveling slowly across the surface as they faded. Carrington had observed a major solar flare. He did not know that at the time, because no one in 1859 knew what solar flares were. He did know that he had just seen something unprecedented, and he made careful notes. What he did not see, because it was invisible from his observatory, was the coronal mass ejection that had been launched outward from the sun at the same time. The CME crossed the 93 million miles between the sun and the Earth in just under 18 hours, faster than any other CME ever recorded, and it slammed into the magnetosphere on the evening of September 1st. The geomagnetic storm that followed lasted for the better part of 2 days, and it was so intense that, on the night of September 2nd, auroras were visible from latitudes that almost never see them. People in the Caribbean reported curtains of green and red light overhead. In Cuba, in Colombia, in Hawaii, in the Sahara, in Queensland, residents looked up and saw lights they had only ever heard about in stories from much higher latitudes. In the Rocky Mountains, miners woke up at 1 in the morning, thinking it was dawn, and began making breakfast. In New York, the brightness was so intense that newspapers could be read in the streets by aurora light alone. The telegraphic chaos lasted as long as the storm. When it ended, the operators went back to their batteries, the line settled down, and the world moved on. Carrington wrote up his observations. Other astronomers documented what they had seen. A connection was eventually drawn between the white light flare he had observed and the storm that had followed about a day later. The mechanism would not be properly understood for almost another century, but the event itself entered the historical record under his name, the Carrington event. The reason the Carrington event matters so much today is not that it caused widespread destruction in 1859. The damage in 1859 was real but contained, because in 1859 there were only 2 electrical technologies on Earth that could interact with a geomagnetic storm: telegraph systems and lightning rods. The first were temporarily disrupted. The second performed slightly more vigorously than usual. Almost nothing else in human civilization was conductive enough on a continental scale to care. That has changed. If a Carrington-class event happened tonight, the consequences would not be limited to telegraph operators in Boston. They would propagate through every long conductor on the surface of the Earth. They would induce slow, large amplitude voltage fluctuations in continental power grids, in transcontinental pipelines, in submarine communication cables, in railway signaling systems, in any structure long enough and conductive enough to feel the changing magnetic field above it. The voltage fluctuations would be small per meter, millivolts to volts per kilometer, but accumulated across a continent-spanning conductor, they could become enormous. Modern high-voltage transformers, the heart of the power grid, are not built to handle that kind of current. They are built to handle alternating current at a precise frequency. Geomagnetically induced currents are slow, almost direct current in character, and they saturate transformer cores. A saturated transformer overheats. It draws excessive reactive power. It can fail catastrophically, sometimes in seconds, sometimes after hours of accumulating damage. The largest transformers in the grid are custom built, take a year or more to manufacture, and there are no spare ones sitting in warehouses ready to swap in. In a Carrington-class event today, hundreds of these transformers across multiple continents could fail more or less simultaneously. The grid could not be quickly repaired. Estimates from a 2008 National Academy study suggested that some regions might lose power for weeks or months. Some studies have suggested years for the worst affected zones. The total economic cost of such an event has been estimated at $1 to $2 trillion US dollars for the United States alone, with similar magnitudes for other industrialized regions. There is a real possibility that a Carrington-class event will happen again. Some studies have estimated the probability of one in a given year at around 1%. Over a human lifetime, that compounds to something not entirely negligible. We have already had near misses. In July of 2012, a CME of Carrington magnitude was launched from the Sun, but it traveled in a direction that missed the Earth by a margin of about 9 days of orbital position. Had it left the Sun a week earlier, it would have hit us. The fact that it did not is not science. It is geometry. It is luck. Forecasters watching the Sun today work with this knowledge in mind. They watch the active regions on the visible disk. They look for the configurations that historically have produced extreme events. They run models that try to predict whether a given flare will be Earth-directed and what its arrival time will be. They issue warnings to grid operators and satellite operators when they see the signs. It is imperfect. The atmosphere of a star 150 million kilometers away is not a clean thing to predict, but it is enough that for routine storms, the storms that arrive several times a month during cycle peaks, we can mitigate most of the worst consequences. The question is whether we will get enough warning of the right kind the day a Carrington-class event finally heads our way again. And whether we will use that warning well. We have had one major test of this in the modern era. It was not Carrington-class, it was much smaller, and it still caused the largest grid failure in the history of North America. On March 13, 1989, at 2:45 in the morning local time, 6 million people lost electricity simultaneously. The geomagnetic storm that caused the blackout had begun 2 days earlier. On March 9th, a region of intense magnetic activity on the visible disk of the Sun launched a coronal mass ejection in the Earth's direction. The CME left the Sun moving at roughly 400 kilometers per second fast, but not extraordinary. Forecasters at the Space Environment Services Center in Boulder, Colorado, watched it leave and issued alerts to the agencies that received their bulletins. Power grid operators were not, at that time, generally on those alert lists. The CME arrived at Earth on the evening of March 12th. It hit the magnetosphere with its magnetic field oriented in the way that allows maximum energy transfer southward, opposite to the geomagnetic field at the dayside boundary. The shield rang. Auroras flared into latitudes that almost never see them: the Florida Keys, the Caribbean coast of Mexico, southern Cuba. In Texas and northern Mexico, residents called local police, convinced that the red glow on the northern horizon was an enormous fire. Above southern Canada, where the auroral oval had expanded much further south than usual, the rate of change of the geomagnetic field reached levels almost never recorded outside of 19th century records. The mathematical quantity that matters here is not the strength of the magnetic field, but its rate of change. A static field, no matter how strong, induces no current in a stationary conductor. A changing field induces voltages proportional to how fast it is changing. And the field was changing fast. The Hydro-Quebec power grid covers a large region of the Canadian Shield, the ancient, geologically stable rocks of the Canadian Craton. The Canadian Shield is a poor electrical conductor. This is an important detail. When the geomagnetic field above changes, ground currents try to flow. In regions with good conductivity, the currents flow easily and stay in the ground. In regions with poor conductivity, the currents prefer to flow through any available alternative, including the power lines that run hundreds of kilometers across the surface. The Hydro-Quebec grid was therefore one of the most vulnerable grids in the developed world. Its long transmission lines ran across some of the worst conducting rock on the continent. When the geomagnetic storm reached its peak intensity on the early morning of March 13th, the voltages induced in those lines were enormous. What happened next happened in stages. The first stage was a series of voltage fluctuations that caused capacitors at a substation called Chibougamau to trip offline. Without those capacitors, the grid lost its ability to compensate for reactive power fluctuations. Within seconds, voltage instabilities cascaded across the network. Generators at the La Grande hydroelectric complex, which supplied much of the province's electricity, automatically disconnected from the grid to protect themselves. Other generators followed. Substations across the province went dark. Backup systems failed in sequence. In 90 seconds, the entire Hydro-Quebec grid had collapsed. 6 million people lost power. The temperature outside was below freezing. Hospitals switched to emergency generators. Traffic lights went dark in Montreal at the start of morning rush hour. The Montreal Metro stopped running, the airport closed, schools closed. Backup generators at industrial facilities failed at higher than usual rates because the storm continued to induce currents through the day, attacking even the auxiliary systems. Power was restored to most of the province within 9 hours. But the recovery from the underlying damage took much longer. Several large transformers had been damaged badly enough that they had to be replaced. A few smaller ones had to be repaired. The cost of the event in 1989 dollars was estimated at several $100 million for Hydro-Quebec alone. The total cost across all North American utilities was probably several billion. Other utilities took notice. Across the world, grid operators began updating their procedures. They installed better monitoring equipment. They built relationships with space weather forecasting agencies. They studied which of their infrastructure was most vulnerable to geomagnetically induced currents, and they designed mitigation strategies. The Quebec event became, for the global power industry, what a few major plane crashes are for the aviation industry: a costly, painful, but ultimately educational disaster. The most important thing the Quebec event did, however, was demonstrate that what had happened in 1859 was not a historical curiosity. The sun had not stopped producing storms of that scale. We had simply built a civilization that was newly vulnerable to them. The Carrington event of 1859 was, by some estimates, about 10 times more intense than the Quebec event of 1989. A factor of 10, when the smaller event already destroyed a continental grid in 90 seconds, is not a comforting margin. Quebec was a warning. It was a small warning by the historical scale of these things, and the world heard it. Forecasting got better, infrastructure got hardier. The vulnerabilities, for the most part, were addressed. Other warnings have followed since. In October and November of 2003, a series of unusually intense solar storms, now known collectively as the Halloween storms, produced auroras visible from Southern California to Greece. Several satellites were damaged, a few were temporarily lost. The Mars Odyssey orbiter, then in orbit around Mars, had to be put into safe mode to protect its instruments from the cascade of high-energy particles. Communication with several deep space probes was briefly interrupted. The International Space Station crew was instructed to take shelter in the most heavily shielded portion of the station for several hours during the worst of the radiation environment. A transformer at a Swedish power station overheated and tripped, briefly cutting power to about 50,000 customers. The damage, compared to Quebec, was modest, but the storms were a clear reminder that the sun continues to produce events of this scale and that they will keep coming. In July of 2012 came the closest near miss in the modern era. A coronal mass ejection of probable Carrington class, possibly even larger, erupted from a region of intense activity on the Sunday. The CME was launched almost exactly outward in a direction that, 9 days earlier, the Earth had been passing through. Because the Earth had since moved along in its orbit, the CME swept through the position the Earth would have occupied and continued into the dark, missing us by about a week of orbital motion. Spacecraft that happened to be in the affected region recorded extreme readings, magnetic fields, particle densities, and energies far above the typical solar wind. Had the CME left the sun a week earlier, it would have arrived at the Earth on a trajectory aimed precisely at us, with an orientation that, by some preliminary assessments, would have produced one of the largest geomagnetic storms in centuries. We avoided that storm not by skill or preparedness. We avoided it because of geometry, because the planet was not in the right place when the storm arrived at the right place. A more recent example, smaller but instructive, came in February of 2022. A relatively weak geomagnetic storm by historical standards, barely worth mentioning, happened to coincide with the deployment of a batch of 40 new low-altitude satellites for an internet constellation. The storm caused enough additional atmospheric drag at those low altitudes to slow the satellites below their planned operational orbit. 38 of the 40 newly deployed satellites re-entered the atmosphere and burned up before they could raise themselves to safety. The financial loss was tens of millions of dollars. The lesson was that even moderate storms, when timed unfortunately, can cost a single company a substantial fraction of an entire launch. These are the warnings the world has been receiving, more or less continuously, for the past 30 years. Some have been listened to. Some have been mostly forgotten. The infrastructure that depends on the absence of a major event is, on the whole, slowly getting safer. The infrastructure that depends on space, on satellites, on long conductors, and continental power grids is growing faster than the safety improvements. But there are still things the warnings did not fully prepare us for, because the magnetosphere is not a simple shield. It has weak spots, it has anomalies, it has places where, even on a relatively quiet day, the protection is thinner than it should be. One of those places is sitting above the South Atlantic right now, and it is getting bigger. If you are still awake, thank you. If you are drifting off, even better. Either way, If this is helping you find some quiet tonight, leaving a like or a subscribe makes it more likely that the next person who needs a calm voice at 3 in the morning will find this video. There's a region above the South Atlantic where the magnetic field is weaker. Astronauts passing over it report flashes of light behind their closed eyes. The region is called the South Atlantic Anomaly. It is not a hole, exactly. The geomagnetic field still exists there. But the field is weaker over this area than it is anywhere else on the planet, and the inner Van Allen radiation belt dips closer to the surface as a result. Where the inner belt would normally sit 1,000 kilometers above the ground, in the area of the South Atlantic Anomaly, it descends to as little as 200 kilometers. That is below the orbital altitude of many low Earth orbit satellites. That is below the orbit of the International Space Station. Spacecraft passing through this region pick up radiation doses several times higher than they would over any other point on the planet. Astronauts working on the ISS routinely report visual phenomena when the station is over. The anomaly flashes of light, brief streaks of color, sometimes lasting a fraction of a second behind closed eyelids. These flashes are not imagined. They are caused by individual cosmic ray particles or high-energy electrons passing through the eye, exciting the retina, and being interpreted by the brain as light. The phenomenon was first documented by Buzz Aldrin during the Apollo 11 mission. Almost every astronaut who has spent significant time in low Earth orbit has experienced it. For most of the satellite era, the South Atlantic Anomaly has been a known operational nuisance. Sensitive instruments are sometimes powered down when a satellite passes through it. Hubble pauses its observations during these crossings. Single event upsets in computer memory bits that flip from 0 to 1 or vice versa because a high energy particle has passed through the chip happen at much higher rates over the South Atlantic than anywhere else. What is more troubling in the longer view is that the anomaly is growing. The South Atlantic Anomaly is now larger than it was when satellites began carefully mapping it in the 1960s. It has also moved westward, drifting steadily across the South Atlantic toward the South American coast. And there is some evidence that it has begun to split into two distinct lobes, one centered roughly over Brazil and another emerging near the southern tip of Africa. What does this mean? The honest answer is that we do not entirely know. The geomagnetic field is generated by flows of liquid iron in the outer core, and those flows are not steady. They evolve. The pattern of the field at the surface is a kind of map of what is happening 3,000 kilometers below, and that map is constantly being redrawn. There is a hypothesis, supported by some computational simulations and some paleomagnetic evidence, that the South Atlantic Anomaly is the visible surface signature of a deep change taking place in the dynamo. Specifically, it may be related to an unusually large patch of reverse magnetic flux deep under the South Atlantic, where the magnetic field at the core mantle boundary points in the opposite direction from what the dipole would predict. Patches like this come and go. The geomagnetic field is full of small irregularities at any given moment, and they all migrate slowly as the iron in the outer core flows. Most of them never grow large enough to matter for life on the surface, but some of them do. In particular, large patches of reverse flux at the core mantle boundary are one of the signatures that, in computational models, sometimes precede a much larger event in the dynamo, a reorganization, a flip. The geomagnetic field has flipped before. We know this because rocks remember. When a lava flow cools, the iron-bearing minerals in it record the direction of the magnetic field at the time of cooling. Seafloor basalts, in particular, preserve a long, detailed record of the field's orientation over the past few 100 million years. And the record is clear. The field has flipped roughly every 200 to 300,000 years, on average, for as long as we can trace. Sometimes the flip is fast, geologically speaking, a few thousand years from start to finish, in some cases a few centuries. Sometimes it is much slower. Sometimes the field weakens, fails to flip completely, and recovers its original orientation in a partial reversal called an excursion. The last full reversal, called the Brunhes-Matuyama reversal, happened about 780,000 years ago. Before that, there had been a long series of reversals at intervals of a few 100,000 years on average. After that, nothing. Not a full reversal. A few excursions, including one called the Last Champ event about 42,000 years ago, when the field briefly weakened to about 5% of its current strength, and the magnetic poles wandered chaotically before snapping back into their original positions. But no full reversal in 780,000 years. The Last Champ event is worth dwelling on for a moment, because it overlapped with one of the more dramatic periods in the recent history of our own species. 42,000 years ago, when the geomagnetic field collapsed to a small fraction of its usual strength, the human beings living across most of Eurasia were not just our own ancestors. The Neanderthals were still alive then, though their populations were declining. Other ancient human groups, including the Denisovans, were still scattered across parts of Asia. The continents were colder than today. Ice sheets covered much of northern Europe and North America. Sea levels were low. And then, over the course of perhaps a few hundred years, the planet's magnetic shield largely failed. A few researchers, most prominently a team in Australia in 2021, have suggested that the Last Champ event may have contributed to environmental changes that affected the species living through it. With a weakened magnetic field, ultraviolet radiation at the surface would have increased. The ozone layer, which depends partly on chemistry that can be disrupted by high-energy particles entering the upper atmosphere, may have thinned. Auroras would have appeared at much lower latitudes than today, possibly as bright displays in tropical skies, vivid enough to be remembered in oral traditions for tens of thousands of years afterward, possibly the origin of certain widespread mythological motifs about lights or fires in the sky. The case is suggestive but not conclusive. Most other researchers point out that the Last Champ event was geologically brief, that life on Earth has survived many similar excursions without much apparent disruption, and that the timing of Neanderthal decline does not match the Last Champ event closely enough to make a clear causal link. The fossil and genetic record is too sparse to settle the question. What is clear is that even in the relatively recent past, the magnetic field has been doing things that no one alive today has experienced. The world was at one point briefly mostly unshielded. It survived. Most of life survived. Some species did not. And then the dynamo, 3,000 kilometers below the surface, somehow recovered. The dipole reasserted itself. The shield came back. That is a longer interval than average. Some scientists argue this means we are overdue for a reversal. Other scientists argue that the data does not show enough regularity to talk about an average interval in a meaningful way. The honest scientific consensus is that the question is still open. But the question is no longer purely theoretical. The geomagnetic field, measured at the surface and from satellites in orbit, has been weakening for at least the past 200 years. The strength of the dipole field has dropped by approximately 9% during this time. If this rate of decline continued unchanged for another 2,000 years, the field would have weakened to less than half its current strength. It would still be a field. It would still deflect most of the solar wind, but it would be much more porous. The Van Allen belts would shift and reorganize. The South Atlantic Anomaly would expand, perhaps swallowing other regions. Auroras would appear at lower latitudes more frequently. Satellites in low Earth orbit would face significantly higher radiation environments. Whether the current weakening is the early phase of a reversal or simply an oscillation that will reverse itself in the next few centuries is something we cannot yet say. The geological record contains both kinds of events. The current state of the field is consistent with both possible futures. What we can say is that the shield is not static. It is alive, in the sense that anything driven by churning convection currents in liquid metal is alive, moving, reorganizing itself, occasionally restructuring. Over the lifetime of any single human, the changes are usually small. Over the lifetime of a civilization, they can be larger. Over the lifetime of a species, they can be enormous. The shield that has been protecting your breath for every minute of your life is still there. It is still doing its work. But it is doing that work as one phase in a longer process that sooner or later, in 100,000 years, or 1,000,000, or possibly much sooner, will reach some kind of transition. What does a transition look like from the surface? We will look at that next. Every 200,000 or 300,000 years, Earth's magnetic field flips. North becomes south. We are overdue. The phrase, "we are overdue," is misleading in the way that statistical statements about random processes often are. The field is not on a timer. The intervals between reversals are not regular. There have been periods in Earth's history when reversals happened every 50,000 years. There have been other periods, the Cretaceous normal superchron, between about 120 and 80 million years ago, when the field maintained the same orientation for 40 million years without a single reversal. The truth is that we do not have a complete physical model of what triggers a reversal, only a long record showing that they do happen. But we do have a reasonable sketch of what happens during one. A reversal does not begin with the dipole field flipping all at once. It begins with the dipole weakening. The simple two-pole structure of the magnetic field, north pole at one end, south pole at the other, starts to break down. The field becomes more complicated. Smaller patches of magnetic flux of various orientations appear at the core mantle boundary. The field as measured at the surface becomes multipolar. It still exists, it is still doing some shielding, but it is no longer a simple dipole. This phase can last several thousand years. During this time, a compass needle would not necessarily point north. It might point in different directions depending on where on the planet you were standing. There might be multiple magnetic poles at the surface, each one a region where field lines came out of the ground or went into it. The familiar geographic correlation, magnetic north roughly aligned with the spin axis, would break down. Then, sometime during this multipolar phase, a new dipole emerges. The new dipole points the opposite direction from the old one. North and south swap. Over the following centuries or millennia, the multipolar irregularities fade, and the field settles into its new configuration. A reversal is complete. The whole process, from beginning to end, takes anywhere from a few hundred to a few thousand years, depending on the reversal. Some are much faster than others. There is evidence, from rocks in eastern Australia, that some past reversals may have taken only a century or two. What would this be like for a civilization living through it? For most of the duration of a reversal, the answer is probably not very different from now. The field would be weaker, solar storms would penetrate more deeply, the Van Allen belts would reorganize, auroras would migrate, satellites would face harder radiation environments. Long-distance navigation systems that rely on the magnetic field, which still includes most migrating birds, many fish, sea turtles, and quite a few insects, would have to adapt or be lost. For human technology, the picture is mixed. We already do not rely heavily on the magnetic field for navigation. GPS makes the magnetic compass mostly redundant for serious work. We rely heavily on satellites in low Earth orbit for everything from weather forecasting to financial transactions. A weakened magnetic field would shorten the operational lifetimes of those satellites and would force us to build new ones with much heavier radiation shielding. The economic cost would be significant. The technological adaptations would be possible. The bigger uncertainty involves the upper atmosphere. The geomagnetic field plays some role in the slow loss of atmospheric gases to space, particularly the lightest gases, hydrogen and helium, but also some of the oxygen and nitrogen that get ionized in the upper layers. With a weaker field, more of the upper atmosphere would be exposed to the solar wind, and more of it would be eroded away. Over a few thousand years, this would not significantly affect the breathable air at the surface. Over a few million years, it could matter. Mars, as we will see in a moment, is the negative example. Mars lost its magnetic field, then lost its atmosphere, then lost its surface water. The process took hundreds of millions of years and is irreversible at human timescales. The Earth, even with a complete loss of the magnetic field, which is not what a reversal involves, would not face a comparable fate within any meaningful planning horizon for our species. But during the multipolar phase of a reversal, there could be something else, a specific kind of vulnerability that we have not had to deal with in modern history. In a multipolar configuration, the simple, predictable shape of the magnetosphere does not exist. The bubble around the Earth would not be a teardrop. It might be a series of smaller bubbles with weaker boundaries between them and the solar wind. There might be paths along which solar wind particles could reach much lower altitudes, perhaps even reaching the surface in some regions. Most likely, the radiation dose at high altitudes, at the cruising altitudes of jet aircraft, would increase. The dose at the surface would still be modest, but the dose at 30,000 or 40,000 feet might be significantly higher than what aircrews currently absorb on transpolar flights. A multipolar field would also do strange things to the ionosphere, the electrically conductive layer of the upper atmosphere that reflects radio waves and shapes long-distance radio communication. The ionosphere is presently organized by the dipole field into regions of different conductivity. With a multipolar field, those regions would be redrawn. Radio communication patterns that have been stable since the invention of radio would change in unpredictable ways. Some frequencies that propagate well today might propagate poorly. Others might propagate better. For most people, day to day, the experience of living through the early phase of a reversal would be subtle. A slowly shrinking auroral oval, expanding southward over a few generations. Slightly higher rates of satellite failure, slightly more frequent calls for caution from space weather forecasters, a compass needle that no longer points reliably north, at first in some regions, eventually almost everywhere. For the species that experienced previous reversals, and many species did, the experience is, as far as we can tell from the fossil record, largely survivable. There is no clear correlation between geomagnetic reversals and mass extinction events. Various theories have proposed otherwise over the decades, but none have held up to scrutiny. Life on Earth has been through hundreds of reversals. Life on Earth has, broadly speaking, not noticed. This is the most reassuring fact about reversals. The shield can flip, weaken, reorganize, and rebuild itself. The sun can continue to send storms. The atmosphere can continue to do its share of the protective work. And the species living under the shield, on average, can continue to live. But this is not always how the story goes for a planet. Some planets, when their shields fail, do not get them back. And one of those planets is the next one out from the Sunday. Mars had oceans. Mars had a magnetic field. Mars had an atmosphere. And then, about 4 billion years ago, something in its core stopped. We know about the oceans because of the geology. Photographs from satellites in Martian orbit show what every geologist immediately recognizes as the worn, smooth contours of ancient shorelines, river channels carved into the highlands, branching the way river systems on Earth branch, sedimentary layers laid down underwater, then later dried out and exposed to the surface as the water vanished. Vast plains in the northern hemisphere that may once have been the floor of a planet-sized sea. Ice still locked beneath the surface today, in quantities that suggest there was once much more. We know about the magnetic field because of the rocks. Spacecraft orbiting Mars have detected remnant magnetization in some of the oldest crustal materials on the planet, the southern highlands, which preserve a record of the magnetic field that existed when those rocks first cooled. The field is no longer being generated, but it imprinted itself on the iron-bearing minerals in the early crust, and the imprint remains. So we know that early in Martian history, perhaps the first 600 or 700 million years, Mars had a dynamo, and that dynamo produced a magnetic field, probably comparable in strength to the Earth's. Below that field, oceans of liquid water sat on the surface. Above that field, a thicker atmosphere held in the warmth of the young Sunday. Then it stopped. The exact reason is still debated. Mars is smaller than Earth. It cooled faster. Its core froze, or partially froze, much earlier than ours has. The convection currents in its outer core, which had been generating the dynamo, slowed and eventually died. The magnetic field weakened. The shield faded. And then the solar wind, which had been blowing past the protected planet for hundreds of millions of years, finally gained direct access to the Martian atmosphere. What happened next took hundreds of millions of years. It is still happening, in fact. The Martian atmosphere, no longer protected by a global magnetic field, is being slowly stripped away into space. The lightest gases go first. Hydrogen escapes most easily. Oxygen escapes less easily, but still in significant quantities. Today, the atmospheric pressure at the Martian surface is less than 1% of Earth's. The surface temperature is well below freezing almost everywhere. Liquid water cannot exist on the surface for more than a few moments before either freezing or evaporating. There is still water on Mars. Some of it is locked in ice caps at the poles. Some of it is in subsurface ice deposits that may extend far deeper than we have yet measured. There may even be transient briny flows in some warm regions during the summer. But the planet that once had oceans, that once had a thicker atmosphere, that once might have hosted the early stages of life, that planet does not exist anymore. It exists only as a memory, recorded in the geology and the magnetism of its surface, for whichever species eventually has the patience to read it. This is the negative example. This is what happens over the course of billions of years when a planet's magnetic shield fails and is never rebuilt. The Earth, by all available evidence, is not in danger of this fate within any meaningful planning horizon. Our planet is larger. Our core is hotter. The dynamo, while it goes through reversals and excursions, has been running continuously for at least 3.5 billion years and shows no sign of stopping. The current weakening of the field is, in the worst case, a sign of an approaching reversal, which is a reorganization, not an extinction. The field will not fade away completely the way Mars's did, but Mars is still worth thinking about tonight, because it is a quiet reminder of what the shield actually does. The shield is not a small thing. The shield is the difference between a planet that retains its water for billions of years and a planet that loses it. The shield is the difference between a planet whose atmosphere stays thick enough to keep liquid water at the surface and a planet whose atmosphere thins to almost nothing. The shield is the difference between a planet on which a particular kind of slow chemistry can play out, the kind that eventually leads to molecules that can copy themselves, and to cells that can divide, and to organisms that can wonder about the sky, and a planet on which that chemistry never quite gets started, or gets started and then is interrupted. Mars almost had that chemistry. The early conditions were there. We do not yet know whether life ever began on Mars in those first few 100 million years. We may eventually find evidence of microbial fossils in the ancient sediments. We may find no such evidence and have to conclude that whatever was happening on early Mars, it was never quite enough. Either way, the story would have been the same after the dynamo stopped. Without the shield, the conditions for surface life ended. The window closed. The window on Earth has been open for at least 3.5 billion years. The shield has not failed, the water has stayed, the atmosphere has stayed. Life has had time and more time to do whatever it was going to do. There is something quietly humbling about thinking through this sequence in a single sitting. 3.5 billion years of unbroken dynamo. 3.5 billion years of iron turning, of currents flowing, of magnetic field lines stretching out into space and returning. Through every ice age and every interglacial, through every continental collision and every continental rift, through every species that has ever risen and gone extinct, through the entire history of multicellular life, through the Permian extinction, when 95% of all marine species died, through the asteroid impact at the end of the Cretaceous, when the non-avian dinosaurs were finished and the small early mammals inherited the planet, through every winter your distant ancestors ever survived, through every fire they ever lit, every cave they ever sheltered in, every star they ever looked up at and tried to name, the shield was already there, always. And the species that finally, after all that time, evolved into something capable of asking what the shield was, that species is yours. That species is, for now, only ours. We are the only beings on this planet who know about the dynamo 3,000 kilometers down. We are the only beings who have ever turned an instrument toward the sun and recorded its magnetic activity. We are the only beings who have ever launched a satellite to the L1 point to watch the solar wind approach. We are the only beings who have ever calculated the trajectory of a coronal mass ejection, who have ever issued a warning, who have ever, in this entire history of our planet, said out loud the words for what is happening above us. Other species sense the shield in their own ways. Migrating birds appear to use the geomagnetic field for navigation in ways that biologists are still working out. Sea turtles seem to imprint on the magnetic signature of their hatching beaches and to return to those beaches as adults using cues we do not fully understand. Some bacteria contain tiny chains of magnetite crystals that align them with the local field, allowing them to navigate the muddy bottoms of ponds. The field is woven into the biology of dozens of species. They live in it. They use it. They have lived in it for as long as they have existed. But you are the one watching it. You are the one, tonight, listening to a slow voice describe what it does. This is part of what it means to be conscious on this particular planet at this particular moment. We have only existed as a species in the form we currently take for about 300,000 years. We have only had agriculture for about 10,000. We have only had astronomy as a serious discipline for a few thousand. We have only known about the structure of the geomagnetic field for 150 years. We have only had real-time solar weather forecasting for 50. In the lifetime of the dynamo, our entire civilization is the equivalent of a single afternoon. The shield has been turning for 3.5 billion years. We arrived, looked up, and within a single human eye blink of geological time, we figured out what was happening over our heads. That is not nothing. That is, in fact, one of the more remarkable things any species on this planet has ever managed. It is also, in the larger view of the story we are telling tonight, an almost imperceptibly small thing. The shield does not care that we have figured it out. The sun does not adjust its behavior because we are watching. The iron in the core will continue to turn whether or not we ever launch another satellite. The next reversal, when it comes, will not consult us. The next Carrington event, when it comes, will not announce itself with any more drama than the last one did. What we have done is make ourselves slightly less unprepared. We have built the instruments, we have done the science, we have written down the patterns, we have placed a tripwire at the L1 point and connected it to alarms in control rooms around the world. We have improved the transformers. We have hardened the satellites. We have, in some small but real way, raised the chances that when the next big storm arrives, the lights will stay on for slightly longer than they would have otherwise. That is what a civilization can do in the face of the kind of forces we have been talking about tonight. Not stop them, not redirect them, not negotiate with them, just understand them, prepare for them, and continue. And then go to bed. The storm is still coming, somewhere on the surface of the Sunday. The knot is still tightening. In a matter of hours or days, it will snap. A wave of plasma will leave the surface and start the 18-hour journey toward your hemisphere. Forecasters will see it leave, alerts will be issued, power grid operators will check their systems, polar flights may be rerouted, some satellites may go into safe mode, and then the wave will arrive at the magnetopause 90,000 kilometers above your hemisphere. The shield will compress, voltages will rise in long conductors, the auroral oval will expand. If you happen to be in the right place at the right time, you may see the sky over your head turn green. Probably you will not. Probably you will be sleeping. The wave will pour into the magnetosphere. Some of its energy will be absorbed by the Van Allen belts. Some of it will be carried down the field lines to the polar atmosphere, where oxygen and nitrogen molecules will glow and fade. Some of it will be dissipated as heat in the upper atmosphere. A small fraction will reach the surface as induced currents in long conductors. Almost all of it will be deflected, absorbed, converted, dispersed. You will not feel it. You will sleep through it. In the morning, you will wake up, you will get out of bed, you will make coffee or tea, or you will walk straight to the window and look at the sky. You will not remember this video. You will not think about the magnetic field of the Earth. You will not think about the molten iron 3,000 kilometers below your feet, still spinning, still generating the lines of force that wrap around your house and your city and your continent. You will not think about the dynamos of dead planets. You will not think about Mars. But all of it will still be true. The shield will still be working. The sun will still be active. The Van Allen belts will still be drifting silently overhead. The bow shock will still be 90,000 kilometers out. The auroral oval will still be pulsing softly around the poles. And on the next night, when you lie down again, and on the night after that, and on the night after that, the same invisible, quiet protection will still be in place, older than your species, older than every species, older than the existence of an atmosphere thick enough to breathe, wrapping itself around every breath you have ever taken. For tonight, for tomorrow night, for as long as the iron keeps turning, 3,000 kilometers below, sleep well. If you stayed with me, leave a single word in the comments. A place, a thought, a feeling. I read every one. sleep well.